Hello, and I'm Emily from emilylearning.com. So in this video, I'll be sharing with you what's tested in the topic of electromagnetic induction. So let's look at the summary of it now. Before I go on to our topic, I would like to share with you some of the resources that I've created recently. So one of it is the O-level physics formula. So in this blog article, I go through or I list down all the physics formulas that you need to learn from each topic. Okay, I've also provided a list of physics definitions here. So you'll find all the common definitions that you need to know for your O-level physics exams. And you can find them at this link here. So I provide the link in the description below. I also provide individual links for this blog post on the O-level physics formula and the O-level physics definitions. Okay, so now let's go back to our topic. The best way to look at what is being tested is by looking at the syllabus. So now let's take a look at the O-level syllabus and let's go straight to the topic on electromagnetic induction to find out what's tested in this topic. Alright, so let's look at that what's tested in electromagnetic induction line by line. So in part A, you are asked to deduce from Faraday's experiment on electromagnetic induction or other appropriate experiments that a changing magnetic field can induce an EMF in a circuit, that the direction is opposes the change producing it, in other words is Lenz law, and the factors that affect the magnitude of the induced EMF. Okay, so basically the first thing you need to know about Faraday's law is, okay, if there is a change in magnetic flux linking a coil, an induced EMF is produced. Okay, so very important keyword is you need to have a change. No change in magnetic flux or magnetic field lines linking a coil or linking a conductor, then there will be no induced EMF. In other words, right, if I put a magnet inside a coil, okay, there will be no induced EMF. Okay, but if I were to move the magnet, then there will be an induced EMF. So maybe let me draw out a diagram. So for example, I have this. So the back of the coil, I write it as ... all right? So I'm going to connect this to a galvanometer. Okay. Okay, so now I have a magnet, right? So for example, this is a magnet. If I were to just place the magnet here by itself and not move it, so if I keep the magnet here and not move it, there will not be any induced EMF because there's no change in magnetic flux linking this coil here, right? Okay, so no change, no induced EMF. But now, if I were to move the magnet into the coil, you'll notice that there will be a deflection in the galvanometer. So if I move it in, there will be a deflection. If I move it out, there will also be a deflection on the galvanometer, but in an opposite direction. And what is the direction of the current induced? Well, it depends on the Lenz law. So in Lenz law, it says that the direction of the induced current will oppose the change producing it. So what we would do is, this is a north pole. So if it is going in, right, if the magnet is going into the coil, then this at this side of the coil, an opposite it will try to oppose this motion, right? So it will have a north pole being created here. So the direction of the current that is induced will have a north pole created here so as to oppose the movement of this magnet in, because like poles repel. So if it's trying to go in, you're trying to repel it. Okay, so now this is a north pole now. So now next what happens is how do I know what's the direction of the current? So if to do so, right, you will make use of your right hand grip rule. So your thumb must be pointing in this direction. So use your right hand, thumb point to this direction. Look at your fingers. You notice that your fingers are pointing downwards. Your second, third, and fourth and fifth fingers, they are pointing downwards. This means that the induced current is in this direction so as to create a north pole here. All right, so next, what do you do? So now I know that the current is moving this way, right? So I know that the current is moving this way. So I know it will go down and this way. Okay, so now I know that this is the direction of the current then. Okay, based on the right hand grip rule. Okay, similarly, if I were, so now let me erase this off. Okay, and I'm going to draw something else. Okay, so instead of having the magnet going in, I will have the magnet going out, right? So let me draw it. So I have a galvanometer. So I have a magnet now. Similarly, here's the North Pole, here's the South Pole. Now what I'm going to do is I want to move the magnet outwards, right? So once I'm going to move the magnet out, you think about it as once it is moving here, this coil, so by Lenz law, okay, it will try to keep the magnet inside, right? So if it is trying to move outwards, so when it moves outwards, you can think of it, this is a North Pole. When it moves outwards, this is your magnet here, okay? So it is moving outwards. So to try to oppose this motion, what happens? Well, the coil will try to attract it, right? So in order to attract, it needs unlike poles. Unlike poles attract. So there will be a south pole here that is being induced. Okay, there's be a south pole here. So next, let's use the right hand grip rule. So now take out your right hand. Your thumb must be pointing to this direction. Now look at your fingers. You notice that your the other fingers are pointing upwards, right? Okay. Oops. Sorry. So in other words, wait, hold on. Okay. So that in other words, right, the current should be moving in this direction. Okay. So that is how you make use of part 2, determine what is the direction of the induced EMF. So basically, you need to remember that it will try to oppose the change, okay, that is producing the induced EMF. So in this case, it is the moving magnet, right, that is producing the induced EMF. So the induced EMF produced will try to oppose it. So if it's the magnet trying to go out from the coil, it will try to attract it. If the magnet is trying to go into the coil, it will repel it. Okay, and you determine the direction. So firstly, you need to determine where's the north, where's the south pole to oppose the motion of the magnet. Next, you make use of the Lenz, the right hand grip rule to determine how the current flows. In part 3, the factors affecting the magnitude of the induced EMF. So if I want a greater EMF, right, then I need a greater change in the magnetic flux linking the coil. So in other words, I need to move the magnet faster. Okay, another way is to have more coils. Okay, so I have more turns in this coil. Okay, that will also increase the magnitude of the induced EMF. All right. Next, let's look at part B. So what do you need to know for part B? Well, you basically need to know the simple form of an AC generator and the use of the slip rings. So basically, I know how an AC generator looks like. Okay, a simple diagram. And then what is the purpose of the slip rings? All right. In part B, you are supposed to describe a simple form of AC generator, rotating coil or rotating magnet, and the use of slip rings when needed. So this is a simplified schematic of an AC generator. So you have a coil, okay, that is being placed in between two magnets. So this coil will be turning. So what causes it to be turning? So for example, let me give you a simplified example. So if we are talking about the hydroelectric power, there will be a turbine that is being turned by the moving water. So and this this turbine, when it turns, it will cause this coil here to turn as well. So you have this coil that is moving and it is in between between magnets. Okay, so in other words, right, when this coil is moving, we have this coil constantly cutting the magnetic field lines, right? Or we can say that there is a constant change in magnetic flux linking this coil here. And when there is a change in magnetic flux linking the coil, there will be an EMF that is being induced. All right, and there will be, so in the effect of having a turning coil, okay, between these two magnets is we generate induced EMF, or in other words, electrical energy is produced. Okay, so the product of the turning coil motion in a magnetic field is electricity. Okay, so because we are producing electricity, to find the direction of the electricity or the current that is being produced, we will make use of Fleming's right hand rule. Okay, so take note, we use Fleming's right hand rule when what we want to find is the direction of the induced EMF. All right. Okay, so basically, if you want to look at what is the direction of the induced current, okay, what we need is to know how this coil is moving, right? So to determine how the coil moves, you need to, the question needs to tell you the direction. So let's assume that the coil is moving in this direction. Okay, so in other words, right, the left side of the coil is moving upwards, right? So motion is pointing upwards. So if you use your Fleming's right hand rule, the thumb should be pointing upwards. Okay, then magnetic field is from north to south, right? So your second finger should be pointing to the left. Okay, and you take a look at your third finger, it is pointing this way. Okay, so therefore the direction of the induced current will be in this direction for the left side of the coil. Okay, and if you have to apply Fleming's right hand rule to this side where the coil is moving downwards, okay, downwards, so thumb point downwards, magnetic field is still from right to left. You'll notice that your middle finger will point this way. Okay, so the current will be in this direction. Okay, so in other words, right, the current will be moving here. Okay, so in this direction. So in the external circuit, this is how the current will flow. Okay, and why do we call this an AC generator? This is because the current generated is an alternating current, right? So think about it. This coil is moving this way all the time. So this portion of the coil, okay, will after some time be at this side, right? And instead of moving upwards, it will move downwards. So if it is moving downwards, then the direction of the induced current will be reversed. So your current will be moving in the opposite direction. So an alternating current is one in which the current changes its direction at regular intervals. So therefore, we have an AC current that is being generated inside this coil. Okay, so this is basically how the AC generator works. Okay, so you also need to know the slip rings, okay, and their purpose. So I've also wrote down the purpose of the slip ring in my blog post on the list of definitions for O-level physics. So do check that out. Next, you need to be able to sketch a graph of voltage output against time for a simple AC generator. So basically, right, the voltage output versus time. So this is time and this one is the voltage. So how it looks like will be something like this. Okay, so you will have maximum voltage generated. So we have maximum voltage generated when the coil is horizontal. Okay, and when the coil is vertical, okay, you will have the induced current at 0. This is because the direction of motion, okay, is parallel to the magnetic field. So there's basically no cutting of the magnetic field lines momentarily. Okay. Okay, and what affects peak voltage? There are some factors. If you use a stronger magnet, the peak voltage will increase. If you have more turns in this coil, the peak voltage will also increase. If you are to turn it faster, your peak voltage will increase, and at the same time, the frequency of the current will also increase. Okay, so take note. So when you turn faster, two effects, right, on the graph. One of it is you have a higher induced voltage, so your peak voltage will become higher. And another effect is that the frequency will change. So instead of having maybe T, this is T, right? So for example, one period is big T. Now one period could be lesser than big T when you turn faster. All right. Next, let's look on to part D, where you need to be able to describe the use of the cathode ray oscilloscope or CRO to display wavefronts and to measure potential difference and short intervals of time. So basically, what you need to do is in a cathode uh, ray oscilloscope, okay, there will be a display. Okay. So depending on the settings, right, the horizontal axis represents the time base. Okay, and usually the question will tell you, so 1 unit, so this is 1 unit, so 1 unit on the horizontal axis, maybe it represents 3 seconds. Then the vertical axis, maybe 1 unit represents maybe 3 volts or 5 volts and so on. And you need to be able to interpret waveforms on this cathode ray oscilloscope, or given some information, you need to be able to draw the waveforms. All right. All right. So now we have covered the AC generator. Next, let's move on to the transformers. All right. So in part F and part G, basically it is on transformers. So we need to know, what you need to know is that the transformer works based on the electromagnetic induction. So you can step up or step down a voltage by means of a transformer. So let me talk more. So a simplified diagram of a transformer looks like this. Okay, and this is usually the primary. Okay, and this is the secondary. So let's look at this. Then this one is the secondary. Maybe let me draw, maybe, oops, directly. Okay. Okay. So for a transformer, right, what it does is it can either step up or step down a voltage. So if there are more coils in the secondary coil, so if because if you look at here, there are more coils here, right? So this is the secondary circuit. So if there are more turns in this coil here, you are actually stepping up. So you will increase the voltage. Okay, if conversely, if you have more turns in the primary coil than in the secondary coil, then it will be a step down transformer. In other words, you are decreasing the voltage. All right. Okay, so how does a transformer works? Well, it works on the principle of electromagnetic induction. So recall in the chapter on electromagnetism, we learned that um, if there's a conductor that carries a current, then it will generate a magnetic field. Well, so in this, okay, so in the primary circuit, there is a AC current, okay, that is produced maybe from the power station and so on. Okay, or basically you already have this current here. So because there's a current moving through here, okay, and this is an AC current, that means the EMF is constantly changing. Okay, then therefore you will create a constantly changing magnetic field. And because I have this iron coil here, there will be a constantly changing magnetic field that links the primary circuit to the secondary circuit. So initially there's no current here, right? So the changing magnetic field, okay, will ele- um, result in an EMF being induced here, okay, in the secondary coil. So that is how you have electricity or potential difference being induced at this side of the coil. Okay, then how does it step up or step down? Well, it depends on the number of turns. Let's assume that I have 100% efficient transformer. That means there is no energy loss to heat or eddy currents and so on. Okay, and all the energy here are transferred to the secondary coil. Then in the number of turns is proportional to the potential difference. So you make use. So we are now at part G. So we have this formula here. Okay, and for a 100% efficient transformer, right, the power at the primary circuit and at the secondary circuit should be the same. So primary and secondary should have the same power, right? Okay, so remember power is equals to V times I. So Vs Is equals to Vp Ip if it is 100% efficient. Okay, so the power in the secondary circuit will be equals to the power at the primary coil if it's 100% efficient. And because of that, you you notice that the higher, because the power remains the same, right? So the higher the potential difference, the lower the current. So therefore, it is equals to IP over IS. Okay, so potential difference and current are inversely proportional to each other for 100% efficient transformers. All right. All right, so then you must be wondering, why do we need a transformer? Well, there are some appliances that requires a certain voltage. Okay, so in order to do so, and our electricity in Singapore is transmitted. Okay, so when it reaches our home is at 240 volts, right? So if I have an appliance that need lesser than 240 volts, then I will need a transformer to step down the voltage to the required voltage. Okay. There are other reasons why you use transformers, particularly at maybe power station. So at power stations, right, before the electricity leaves, okay, and get transmitted in those cables, they are actually step up to very high voltage. The reason why we step them up to high voltage is because the higher the voltage, the lower the current, and therefore there is less energy loss to heat, right? There will be less energy loss to heat. So because power loss in cables is equals to I square R, or energy loss to in okay, so energy loss, or I can call it as the power lost in cables, okay, due to the resistance, okay, it's equals to I square R. So the lower the value of I, the less power loss to heat due to resistance of wire. So that is why when we are transmitting the when we are transmitting electricity, we always like to transmit it at high voltage. But once it reaches the substations, okay, it will be stepped down to maybe 240 volts before going to our home, because it will be dangerous to have such a high voltage. So therefore, it will be stepped down. Okay. There's also other reasons. So remember that, right? Heat loss or power loss in cables is equals to I square R. Okay. So the lower, so when you transmit at lower current, right, you will need cables that are less thick. Okay, but if it is a very high current, you need very thick wires. If not, you have a lot of heat loss. Okay, so that is another reason for it. All right, so basically that's it for the electromagnetic induction topic. So if you're interested to learn in detail on what's tested in O-level physics for the topics on electromagnetic induction, electromagnetism, as well as magnets, I do have a course, okay, that is available. So in this course, you will learn these concepts in detail, and I'll also go through sample questions so that you'll be able to tackle your exam questions. So I'll provide a link to the course right below, so do check it out. Thank you for watching this video. Do subscribe to keep updated with our latest videos. And if you are interested, we do have an entire playlist on all the topics tested in physics O-level, where we share with you what is tested in detail. Okay, in addition, if you want to learn in detail, do check out our courses on Udemy. Bye and see you.